Okay, this is the video for fifth period Trig Calc A. We're gonna finish up the last page of the notes for chain rule. Here we go. Example 363. This example has us using both chain rule and product rule together, so be very, very careful. We see f of x defined as a product first and foremost. There's the x squared times sine of 2x. X squared is not plugged into any other function, which is why this registers as a product. The sine function does have a 2x plugged in, so when we eventually find the derivative there, we'll need the chain rule. But f prime has us taking derivative of the first component multiplied by the second component of the product, unmodified, and a plus sign followed by the original first component, now times the derivative of the second, and this is where the chain rule comes in. We know a derivative of a sine in general is cosine. If we started with sine of 2x, we now have cosine of 2x. Times 2 is the chain rule. That's your derivative of the 2x. This line here is an answer, but I also have a version that has been factored a bit. And as always, feel free to pause the video to copy down notes as you go. Example 364 features more chain rule, but also some foreshadowing to what will be our next topic, something called implicit differentiation. We see a variable s, a function s, described as the tangent of theta. And okay, so on its own, this does not seem like something that would require chain rule, but we want to find derivative of s not with respect to the theta that we're seeing, but with respect to t. And this is where the alternate definition of chain rule can be perhaps a little bit helpful. I'm going to refer back to that right now. I'm looking at the bottom of that first page of chain rule. If I want a dy dx, but y is in terms of a variable u, I can start with dy du and then chain from u to x with du dx. That's what we're going to be doing in our current example. Go bring that back up. So to find my derivative of s, I start with just a derivative with respect to theta. I had tangent theta, we're going to make it into secant squared theta. At which point I recognize that I really wanted to go in terms of a variable t that's not even here. And that's okay. What's really perhaps happening behind the scenes is that our theta might be some formula of t. It might be theta equals something with t. So with that in mind, I'm going to treat theta as a plugged in function to the original tangent. And that's where chain rule comes in. I can go with my secant squared of what we started with times the derivative of this plugged in theta in terms of t. So I don't know what that looks like exactly. The best I can do is say d theta dt would be the derivative of this theta. But in writing that down, I have used chain rule. And luckily, we're saved by the prompt here. I have this expression that doesn't seem like we can get too much further with it, but they do tell us to find the value of it when theta is equal to pi and d theta dt is equal to 3. So I could just make a couple simple substitutions. Literally change theta to pi, replace d theta dt with 3. Okay. We should still know our trig circle. Secant of pi is -1. So we square it. We end up with this expression is just 3. Example 365, the purpose here is to remind us that even with chain rule in play, we still may have to find beyond a first derivative into a second derivative and even beyond that potentially. So that's what we're going to do here. I start with the derivative of cotangent, and I don't need any chain rule here because the only thing plugged into cotangent is a regular x. You can just use our basic shortcut rule. Don't forget the negative. You might notice I've written this expression, the dy dx, a little different compared to what I usually would. I've modified the notation to put the exponent outside parentheses because I'm gearing up for taking a second derivative. Here I have a polynomial term. I have something squared, but we have an entire trig function plugged into that. Instead of x squared, it's an entire cosecant squared. And that's where chain rule comes in. So for my second derivative, we take our 2 exponent out front. The exponent on cosecant is now 1. I don't even bother writing that in. Next, I have to multiply by the derivative of this plugged in cosecant, which again is a rule we should have had memorized from last chapter. And then I can clean this up a bit. There's a couple negatives that can turn into a positive. And there's your final answer. Final example, 366. These problems are pretty typical on the AP test, and we'll see them as well. We don't know the actual definitions of f or g or their derivatives, but we have certain values of those functions for given values of x. We can use them to evaluate some of these complicated derivative expressions that we are seeing here. For me, with problems like this, I don't really worry about what x is going to equal, at least not until I've already figured out the general rule for whatever derivative I need. You can see that in my part A. I'm concerned firstly with just finding a derivative of f of g of x, which is g plugged into f. So thanks to chain rule, we know it's going to be f prime with the same g of x plugged in times derivative of that plugged in function, the g prime. And once I have this statement written out, I'll start plugging in numbers. I want x to be a 1. So everywhere that I see an x in this previous expression, I replace it with a 1. And now I have f prime of g of 1 times g prime of 1. And we can start using the table. G of 1, according to the table, is a 2. G prime of 1 is a negative 1. So I update the expression to match, which leaves me with yet another table value I need to go grab. F prime of what's now a 2, well, that's going to be 6. So 6 times negative 1 gets me to my result. Part B, I'm going to take the derivative of what's really g of x to the 1/2, which you can think of as the entire g function plugged into a square root function, an x to the 1/2 function. So I'm using my same polynomial shortcuts we're accustomed to, with g of x still plugged in there. And again, times g prime. And then once I have the general derivative mapped out, I can plug in 1s for x's, g of 1. Actually, is this a mistake here? This g of x right here. Oh, sorry, we're plugging in a 2. That's my mistake. But yeah, this g of what's going to be g of 2 here, we're plugging in. G of 2 is a 1. G prime of 2 is a negative 3. And we clean it up from there. Part C, more of the same. Derivative of the g function, except instead of just an x, we have x plus f plugged into g. Well, I'm going to still start with g prime of whatever the initial plug-in was, multiplied by the derivative of that plug-in. Be careful here. I see a function of x as well as a copy of x. We already know the derivative of x is just 1. The derivative of f of x, we would call f prime of x. So I do have a 1 plus f prime in here. And now that I've gotten that far, we can replace all the x's with 1s. Here's what that looks like. There's some further simplification needed inside the g prime portion of the term, but use the table to finish that up and make sure you get the same place I got. We close it off with one more example combining chain and product rules. We see a product g of x squared times separately an f of x. The f of x is not plugged into another function. It is a product with another function. So you can see me writing out my general product rule first. Okay. And when I find the derivative of g of x squared, I am using chain rule, but I have to take that entire derivative times the other portion of the product unmodified. And then I switch roles over here. I take the g of x squared, I leave it as is, multiplied by f prime. And now again, we're plugging in 2 for all the x's throughout here. Once we have that mapped out, we plug in values from the table. We should end up with 18. And that concludes the video. If you have questions, you can email me or ask me in class. Thank you for watching.